you everyone for being here. I intended today to talk about, as Fernando said, the interest and how we can reduce motor models and what can we do with that. The agenda here I can share. I will start by introducing a little bit the company I work for, which is a research and technology organization, and the electric system department inside that company where we work. Then a few slides on the motivation. Why should we work on model reduction, and with a focus on the issue of motor currents modeling. Then we can switch to the results and the method that we followed, and I can share a few results before actually concluding the presentation. So to introduce IFP Énergie Nouvelles, this is, as I said, we are a research and technology organization, both public sector research innovation, also a training center, and also part of an industrial group with the outlets. It's more than 1,500 people and has a very international scope. Considering a few key figures here, we have more than 10,000 active patents. We are very high ranked in France on that, and as we are the third, lots of international publications and lots of doctoral students. So yeah, we have quite a big activity, and a part of it, a significant part of it, is about mobility. Our activities in mobility and electrification represent, I gave you here a few figures, but what's interesting, more than 35 PhD students, 300 people, and a lot, again, of active patents. So just to say that we are a research organization, but also linked to the industry, and we are in between academic works and really the industry. We tend to work as a passage for the technology. The goal is pass the technology from academic to reality. So now, with a focus on the electric system department. When we say electric system department, we take that aspect quite globally, meaning that we can specify and propose innovative electric system for traction or electrified turbos, for example, here. We design, we simulate, and we prototype ourselves the electric motors and the power electronics. We also control and optimize the electric system. We have our own systems of control, which is very developed here. And also we integrate benches to test benches, I mean, to evaluate and validate the system that we developed. So this is quite wide on the area. I said it before, the objective is to go from innovation to the markets at some point. This is our position in the TRL value chain. TRL value is, for those that don't know, a score of maturity of any kind of prototype or product. 9 being a fully mature product that is in sale. 7 being a functioning prototype in real conditions. So what I can say here is that we, on the electric systems, try to find partnerships to source advanced components. We do not deal with magnets or really switching device for the power electronics here ourselves, but we tend to make partnerships to be sure that we are in advance on those aspects. Then our work starts, and we design innovative parts whether it's for electric motors, power stages, and the controls that we integrate in real systems. And then we can validate fully the system. Once we have reached this point, because we won't sell anything ourselves, we look for industrial partnerships to find some value in this new technology. So just a quick thing also, this is mainly, this activity is mainly towards, for us, automotive traction and fuel cell application, which is mobility business unit. In the electric system department, I said it a bit before, we have all the skills needed to simulate and design and validate the prototypes. From system analysis, motor 3D design, electronics design, mechanical prototyping, the controls, and the experimental validation. This is a key point to me because we have all of that skills in a relatively not small teams, still dozens of people, but it stays small. So we can benefit from interaction between these different skills and people. So let's go to the motivation and the work on model reduction. It's important to understand that we work on model reduction because also we have people that know about the real physics, the advanced physics, and people who know about experimental. And model reduction, we'll see, is somewhere in between. Basically, what's the motivation? The idea is you have a powertrain, you want to make it better. You want to optimize it, whether you're talking about efficiency, power density, noise, ecological impact, anything you like. There are two main approaches there at the ends of the spectrum, which is the experimental testing. This is real life, so this is the reality. You cannot do anything more precise, I would say. And also you have very high fidelity models with finite elements, 3D computations that can come in some cases quite close to the experimental results that you can have. However, whether you're optimizing on the hardware or software point of view, testing, experimental testing costs a lot of money. It takes a lot of time. And the high fidelity models, they are great for accuracy, but generally speaking, they are not really practical and take quite some time to simulate. So in between, we try and find reduced models somewhere in between experimental testing and high fidelity models that will allow us to iterate on the optimization of the hardware and software in a reasonable time. This is a key point of any powertrain design, actually, from my point of view. Here, I will take the prism of the control laws, which is, this is quite, it's often seen as simple, driving an electric motor, but optimizing it is actually quite a challenge. The objective here is we want to replace what is usually done now, meaning evaluate different control laws on the bench. We want to replace that with simulation as much as it is possible. What are the performance criteria we aim for? Efficiency, of course, but also the constraint, DC ripple, the noise, vibration, torque ripple. If you have a control law that you cannot compute in a reasonable time, CPU load becomes a real issue, and all that. The idea here, with the standard control, you can change, of course, the switching frequency, and you will move between motor losses to inverter losses whether you choose to have a low switching frequency or a high switching frequency. Here, I'm going into this detail because the objective is not choosing it between and finding the best efficiency. It's going beyond that choice and finding other PWM controls, plus with modulation control, that will optimize this. This is a generic workflow that you can use. You have a low control, sorry. You have a control low, you use it to evaluate through models the performance. That helps you go through a very wide space of research, and then you can optimize it. So in the end, when you work on here model reduction for control low optimization, you have two objectives. The first and always is find the best possible time accuracy trade-off. It's quite easy to understand. The time is key to evaluate lots of configurations, but accuracy needs to be enough so that the evaluation I make are still relevant. You have two key points on the controls here. How to compute motor currents here. You have the inverter and the currents. I want to be very precise on this current shapes, and afterwards the losses themselves, which are a challenge, another challenge by themselves. So I wanted to introduce a bit the motor currents modeling issue, the way I see it. So everything is a bit more clear for everyone later on. This is the ideal case. This is not the real one, of course, of driving an electric motor. You start from the torque request pedal that's read by a CPU board. You would ideally apply sinusoidal voltages by the inverter, and you would obtain through a perfect motor sinusoidal phase currents. That would give you a perfect torque, which is remarkably constant. However, this is not real life, and there is one thing that comes in first, which is the space harmonics. The motor themselves, especially when you are talking about a synchronous reluctance motor or any topology with a bit of novelty these days, you usually have quite some important space harmonics coming from the motor structure itself that will create two things: harmonics in the current. Here it's harmonics of the order 5 and 7 with respect to the fundamental frequency. And it will result in at least harmonic 6 in the torque that is produced. This torque is already an issue as it can make the system in which the motor is embedded vibrate, and you can have some noise issue. And it reflects also on the currents themselves. Next step, real life is PWM, pulse width modulation. We do not have the inverter that can provide sinusoidal voltages, so we need to make it like this, a stair. And then we reproduce a globally sinusoidal current, but with usually quite a lot of high frequency components. This you can find also sometimes on the torque, depending on the conditions, this high frequency part, but mostly this high frequency in the motor will add motor losses. So what you can see here is that depending on, I know I want a sinus, but you can understand that the stairs here I have several ways of doing it, and this will give me different ripple, and this will give me different losses. But the stairs also impact the inverter losses. So this is all about the compromise in between and where to find the optimal solution. Actually, the PWM setup, which is choosing the stairs for shapes here, it has quite an infinite possibilities of setup. You can change, I said it before, the switching frequency, but you can change if it's really constant or it moves in time, or even if it's random. You can modify the strategy. You can overmodulate more or less. You can have synchronized. There's really lots and lots and lots of possibilities there. Here, the illustration shows you what's happening if you go with higher and higher switching frequency. You can see that the current shape becomes better and better. So the motor losses will be reduced when the frequency increases. However, the inverter losses, as I said before, will increase. This kind of computation, and especially motor losses, this is very time consuming. So if you try and evaluate tens of thousands actually of possible configurations in which you try and find your optimal control law, this is not really realistic for motor loss evaluation with finite element computations. This is why accurate simulations here on motor losses, but still fast simulations, are a game changer for control laws optimization. So we went through the why and a bit of the what. So let's see now the results and how we did it. About motor currents. I will start with the results. Finite elements computation of high frequency currents here. This will take you roughly 10 minutes depending on the settings. You can use time-based reduced model as we did, and this time will go to 5 seconds. But you can also use a second level of model reduction, which is using a frequency-based approach. And with that, we reach 0.1 second. As you can see, difference between 10 minutes and 0.1 second. This is quite wide, and this is very useful to be able to compute actually exactly the same currents as with the finite elements. We have a very important gain here. So the question is, how did we proceed? Let's take a look. Globally, the methodology is always a bit the same with some variations, but we take some knowledge from finite element computation and we try to combine it with an analytical equations, Depending on the level of accuracy, depending on what you're trying to modelize, at some point you will make different choices. But it's roughly always the same approach. You extract from a time-consuming simulation the parameters and data that you need. Once you have computed these parameters and data, you combine it with, in the first case, time equations. This is quite a simple one, if I can say so, about linking the voltages, the currents, and here you can see the fluxes and their derivatives have a direct link on how the currents will behave inside the motor. This is a version of the time-based equation for the time-based model, but we also derive this into frequency-based models. It's a bit different. It's a bit more work, and it needs a bit more, some more assumptions and simplifications. But in the end, you have these two kinds of models. Both these models, they were compared against two things: the results of the high fidelity model, meaning magnetodynamic simulation from actually from Maxwell software suite. And also we compared the results against experimental data. So first things first, we built two models, and I said that the frequency-based model has some more simplifications with regard to time-based model. So we wanted to check if we had the same results. You can see here on one given operating point that the phase currents A, B, and C in blue is the time model, and in red is the results from the frequency model when we gave the same voltage input. Results are virtually the same. It's not so obvious on the full phase current, but if you take a look at D and Q currents, here you can see that there is no real numerical difference in between. This is also confirmed when you look at the Fourier analysis of these signals. Both the PWM harmonics here at higher frequency or the special harmonics that I mentioned before are computed with almost the same level. So this is quite good results. In the end, the conclusion is the frequency-based model is perfect for a steady-state study. What do I mean by this? Is that, okay, so I have a frequency-based model. It's 10 times faster than the time-based. Why should I use the time-based model? The issue here is that the frequency-based model, it can only work if your operating point, meaning the D and Q mean currents, are constant. If I go from a load of 20 Newton meter in my motor to a load of 100 Newton meter, that transient cannot be modelized with this approach of this frequency-based approach. However, it's perfectly modelized with the time-based approach. So this is the trade-off you have mostly here. Just a word about the space harmonics I mentioned before. We try to remove it from the frequency-based model, which is actually what's mostly done when frequency-based models are developed. Usually they do not include this special harmonics part. So this is the difference that you get. You can see here that this is really not exactly the same. And also the mean and max of the currents are different. This would be also probably the same on the DC ripple, DC side ripple on voltage and current together. So if we now switch to experimental validation, what we used was one of our test bench inside the IFP Energy Nouvelles. Also, IFPEN design 150 kilowatt motor, and an IFPEN design SiC inverter of 200 kilowatts with our control also. So we have knowledge on simulation from this motor because we designed it. We have knowledge of the bench because we are used to make tests on those. And we also have knowledge of the losses in our own inverter, and we have knowledge of the control load because it's our control. In the end, if you compare the frequency-based model versus the experiment results on the operating point, you can see that the results are globally very satisfying. We have very slight discrepancies here that comes from the fact that on the bench testing, you have a closed loop of regulation of the currents, whereas on the first results before, they were obtained on open loop with a constant command. So this is the case here. There is no closed loop on the frequency model. So this gives you the performance here on high frequency current modeling, whether it's for spatial harmonics, very accurate as you can see, or PWM harmonics, comparing experiment and frequency modeling. So now that we know that the motor currents, we can compute those quite correctly, we switch to the motor losses computation, which is quite a big challenge. The idea is to use the current that we compute to be able to evaluate the losses that goes with that current. And we'll see that that's not so obvious, actually. So here is a quick video of how losses are actually computed in a finite element approach. Each mesh here, we have the B and H fields. And as you can see, when the motor rotates, B and H fields, they move all around. And usually on the traditional losses computation method, we compute, as I said, the field in each mesh, and we can apply a formula, mesh by mesh, to be able to evaluate the losses of the given mesh. Good example of such a formula would be the modified frequential Berthotti formula here, linking the B field amplitude and the frequency with corrected parameters. This will give you, this can give you, if it's properly tuned, quite accurately the losses of a given motor using finite elements. Here, as I said before, we want to use the phase current as the input of our model because we are not using finite elements anymore. So we cannot compute the meshes for every possible control law. So the idea is to use an identification of an equivalent resistance that is a specific model based on the spectrum of the currents. So each current here for a given frequency is given a resistance, and that allows us to compute a good evaluation of the losses in 0.1 second instead of an hour. So this is the generic idea, and now we can look a bit at the results. The first things first was to compare the resistance, the equivalent resistance model with the finite element model results. So what we did was we did a switching frequency sweep with a standard control, SVPWM. So going from 4 kilohertz all the way to 27, if I'm correct, kilohertz. As you can see, finite elements in blue gave us a trend, but the model fit here in red was globally correctly identified, but you can see here that if you go higher in frequency, you will have an issue of a discrepancy here. This is the results we had between the simplified model identified over finite element results and the finite element results itself. Then we switched to the same identify equivalent resistance model, and we compared it to the experiment. In the end, even if it's only less than 100 watts, it's not so much when you look at a 150 kilowatt motor. You can see a difference. The global trend here between the experiment and the reduced loss model was not really perfectly identified. And actually, if you take a look at the results from the finite element models, here you can see that if the reduced model doesn't fit the experimental data, it's also mostly because the finite element models was not perfectly fit to the results. So this gave us the following idea, not really gave us, but we used our kind of backup plan, which is because the model, the equivalent resistance model, is simple. Instead of calibrated on finite element simulation, you can also generate the needed set of data with experimentation, and you can try and fit directly experimental results. So this is what we did. We did the same frequency sweep with the SV PWM, but we did it on a motor on a test bench. As you can see, the global trend here is, of course, better than the previous results. So we trained the model on the SV PWM frequency sweep, sorry. But then we can validate it on other modulations. I cannot go into details in which modulation they are. But you can see that here we have 20 watt error maximum. And most importantly, the trend is correctly identified in between the experiment and the prediction from the simplified model. So basically, we leverage this on several operating points. I showed you in detail one operating point, but roughly we did that for a little less than 20 operating points. These are the results of frequency sweeping for all the operating points. There are three colors, blue, red, and yellow, because we did 3 repeats. As you can see, in most of the case, the repetition is very good. If you look at the spread here, it's roughly it's less than 20 watts on our bench. And these are high power points, whereas here it's lower power, and then you are at 3 watts of variation in between two repetitions. So we kind of trust the experimental measure that we have here. Then we identified the model for each point, and we replayed on those same operating points, but with other modulations again. So this is all bit of the different modulations that we used on all these operating points. And there are 4 colors because this time we did 4 repeats instead of 1 or 3. Sorry. Globally speaking, the results were the following. If we look at the differences between the results from the identified equivalent resistance model and the experiment measurement, here the relative mean error is below 8%, which relates to less than 50 watt of absolute mean error. And most importantly, most of the time the tendencies are really well captured. So this is the key point for control optimization. So I reach here my my conclusion. Thing is, what can we do with this? We have now identified equivalent model for the motor losses. So we have the models, they are identified. We can go back to the simulation and use this fast computing models to evaluate a great number of PWM configuration. Actually, as of today, yes, we can evaluate roughly 50,000 different schemes in an hour of time. Then again, I wanted to underline that when you generate that much data, of course, you can look into it, and that will provide you insight and give you some global analysis on what's interesting and what's not. But I think a key point here and the perspective of work is to find the correct key performance indicators, so that depending on the operating point, you can kind of automatically find the best possible control. This here is a part of the different PWM scheme that we evaluated on our model, and some results that we obtained, illustrating the trade-off between inverter losses and electric motor losses. If you go in higher frequency here, you will have high inverter losses, and it's the opposite with lower switching frequencies. And those are different PWM solutions. As you can see, we can reach some gains here in between different modulations. And this is just a small part of what we can try and optimize. Don't pay attention to the number here. This is more scores at this point. So in conclusion, I would say that, as I said before, model reduction for me is a key approach if we want to optimize the design of hardware and software powertrains, hardware solutions. A good example, I think, was the one that I showed here about PWM controls, because there are quite a lot of degrees of freedom, and we cannot test everything, and we cannot simulate everything with high fidelity models. So this is why we needed to go towards model reduction, which we did, and we reached 1,000 times faster, even 10,000 times faster models without losing that much accuracy. Furthermore, we can use the results and the simplified models also to improve the high fidelity models, because they have less complexity. They will catch a little bit easier the tendencies. You can identify things with that, and that will give you feedback to improve your high fidelity models. And of course, as I said just before, we can now use simulation to optimize motor controls. So that concludes my presentation. I hope you liked it, and if you have any questions, I'm really open to listen and answer. Thank you.